Yeah, Bhumika, over to you.
Yes. So, good afternoon, everyone. It is my distinct pleasure to extend a warm welcome to all of you. This event is organized by Curry Leaf, a math club of MTTS alumni in collaboration with MTTS Trust. Today marks the inaugural talk in our mini series on Lie Algebras. Our distinguished speaker for the day is Dr. Shankar Ilangovan. Dr. Shankar Ilangovan is currently serving as an associate professor in RKMVERI Belur. Welcome to you, sir. We also have a special guest among us. That's our beloved Kumreshan, sir. Welcome to you, sir. As we know, this is a mini series on Lie Algebras comprising 4 talks. In this mini series of 4 talks, we'll explore Lie Algebras with a focus on understanding the various concepts involved in classifying simple Lie algebras over complex numbers. Now I would like to request Kumreshan sir to speak a few words and inaugurate the series. Over to you, sir.
Thank you, Bhumika. It's my great pleasure. My long-term friend, more than 4 decades, Professor Ilangovan is giving lectures. But I think we have a much more important person, Balasubramaniam. Okay. And I hope he will be also requested to say a few words about Ilangovan. As I said, I have known Ilangovan for last more than 4 decades. Maybe he may be able to give the correct
46 years.
date. 40?
46 years.
46 years, right? Okay. See, he is always good at such things. Okay. He can even give the first date on which we met. Okay. His memory is phenomenal. Okay. That's the first thing I always remember about Ilangovan. All right. We have known each other very so well. And knowing is kind of, dedication to students, youngsters especially, all, not necessarily math students, all young students. He always mixes with people, gives them good advice, gives them directions, etc. And when he was in TAFR, then he joined University of Mumbai, later University of Hyderabad. Everywhere, he's perhaps the most loved teacher wherever he was. Okay. And it's a great opportunity for all of us to learn from Lie Algebra, a field in which he has given good, contributed a lot. Okay. So, but my earnest request will be, I would also like, he has a lot of other hidden talents, and Professor Balasubramaniam may be the best person to explain that. Okay. He is not only an accomplished mathematician, he is also a fantastic bridge player, which I have no idea about. Okay. So I think Professor Balasubramaniam may give some ideas. Thank you very much. Bhumika?
Yes, sir. Thank you so much, sir. As Kumreshan sir said that Professor Balasubramaniam knows more about Professor Ilangovan, I request Professor Balasubramaniam to speak a few words.
Okay, thank you. Yeah, exactly as Kumreshan said, that my connection with Ilangovan is of a different thing. I don't think we have discussed much mathematics, but we have played as a team, as a pair, a lot of times, bridge. I mean, that is the one which connects. And again, both of us are interested in gossip. And that's again one thing which connects us. And we at least call each other for at least twice a week to exchange the new gossips, etc. But I have heard from people who have heard his lectures that he is a great lecturer. And I hope that this audience, as well as other audience who are probably in the YouTube, would learn a lot on Lie Algebras from him. Thank you.
Thank you so much, sir. Before we begin the presentation, the talk, I'd like to share a few important instructions to the audience. Feel free to ask questions, but don't unmute yourselves until you're prompted to do so. You have the raise hand button option in the Zoom. Kindly use that. Over To you, sir.
Okay, thank you. Thank you very much. So first of all, thanks a lot to Curry Leaf. I believe this is not just a invitation, it's a privilege and it's an honor for me to be giving this series of 4 talks. And it's wonderful that 2 of my best friends are introducing me. Kumbraya, I know that he has only a power nap for 10 minutes. Balu, I know he has a longer afternoon nap, and today being a Saturday, he's sacrificing his nap and attending. So it's my job to make it worthwhile, not for all the audience, also for my good friend, Professor Balasubramanian. So first of all, we are going to discuss everything over complex numbers. Let me see how big it is. Yeah, this is okay, right? This font is fine?
Yes.
This is fine, sir.
Okay. So all the results, of course, are going to be true for any field, of course. Later on, maybe today, tomorrow, we may not need algebraically closed field, but later on, we may need algebraically closed fields also. To begin with, in complex numbers, we have addition and multiplication, both commutative and associative. Right? The nice thing about addition and multiplication are they are both commutative and associative. And the interesting thing is the fact that this is a binary operation is not only known to mathematicians, even Bollywood seems to know binary operations. So how do we know that Bollywood people know binary operations? Of course, most of you are young. When this song came out, you wouldn't have been there, but you might have heard this song. There is a song which goes, yeah, many of you might have heard this song, 1 2 ka 4, 4 2 ka 1. So this is what is the Bollywood understanding of a bilinear form. And assuming that they meant linear equations, if we solve it, you will see that this is what we have to solve. Luckily, it's not very difficult to solve it. What do we get? We get x equal to -1, y equal to 5/2. So this operation ka is -x plus 5/2y. So this is what this seems to be giving. If we give xy, what we get is -x plus 5/2y. And if we look for these two nice properties, commutativity and associativity, you can see that not only they are not commutative and associative, they seem to be a bit too random. Okay, there is no connection between commutativity of ka and associativity of ka. Xy goes to -x plus 5/2y, yx will go to -y plus 5/2x, seems to be too random, and similarly associativity also is going to be too random. So the reason why we are discussing this ka given by Bollywood, whether it is just for fun or there is something hidden in it, we will see slowly whether it is for fun or it's going to be useful somewhere. And so now we can't leave Bollywood far behind. We have our own agenda. So this is as I mentioned, I won't keep on telling that it's over complex numbers. That's why I'm just writing GLN. These are all n by n matrices with complex entries. And again, we know that we have addition and multiplication. Two square matrices we can add, and two square matrices we can multiply to get another square matrix. Similar to whatever Bollywood has done, we will also try to do something using this addition and multiplication. We define what is known as Lie bracket. So the Lie bracket is going to be a binary pairing on GLN to begin with. What it is going to give? This is the definition: xy minus yx equal to x bracket y is xy minus yx. Okay, so how this comes and all we will discuss a little later. Like we discussed CAR, let us see what properties this satisfies, particularly whether it is commutative or whether it is associative, etc. Everybody fine? So this is what we have defined. GLN is all n by n matrices. Lie bracket xy is defined as xy minus yx. We will discuss the properties of this now. So first, it is easy to see one important thing, that xy is xy minus yx, yx is yx minus xy. So it turns out that Lie bracket xy is minus Lie bracket yx, right? So though it is not commutative, as we would have liked to have nice operations, it is not too random like Ka. This is what is known as anti-commutative. Instead of being random like Ka, this has a well-defined property xy equal to minus yx. So this is anti-commutative. This was the easier calculation. If we want to check associativity, we have to do a little bit more work. This is the question when we want to discuss associativity, whether x comma y, first I take the bracket and then take a bracket with respect to z, or I take yz first and then take x, whether these two are same. This is the question we have to answer. And by the property 1, we know that this is nothing but minus yz. We know that x bracket y is going to be minus y bracket x. So x, y, z in particular is minus y, z, x. So I can take this whole thing to the other side. And ask the question, if I take this sum, whether it is going to be 0. And this requires calculation. Let us do the calculation now. I will just say left hand side. What is this? Xy minus yx z, yz minus zx. Okay. First I have applied xy, we get xy minus yx, and yz is yz minus zy. Now we do the Lie bracket again. Okay. I'm going to be a little bit careless because we know that matrix multiplication is associative. I'm not going to keep putting brackets. We just write xyz minus yxz minus zxy plus zx yzx minus zyx minus xyz. Okay, the first four terms are coming from the first one, and the second four terms are coming from the second.
Yes, the meeting will end with 10 minutes. Yeah, so you need to complete.
See, some message is coming apparently. I can read that remaining meeting time is 10 minutes. I don't know what, it's only for half an hour it seems to be. Somebody should do something about it, one of the hosts. Okay, please take care of that thing. Remaining meeting time 10 minutes is what the message we are getting. Okay, so some terms get cancelled, I suppose. Which are the terms getting cancelled? This is getting cancelled and this is getting cancelled. It is seen that only these terms are getting cancelled, all other terms are not getting cancelled. So what do we get? Minus yxz minus zxy plus yzx plus z. Okay, so for arbitrary matrices, no cancellation is possible now. So we are left with this. But does it have any good structure? Since we are looking for associativity, anti-commutativity was a nice property. Here also we are looking for some good structure. What good structure can you get? If you just take y out here, what do we get? Y into zx minus xz minus zx minus xz. Okay. So I'm just combining the terms with y on the left hand side and y on the right hand side. And what we get is y into zx minus xz minus zx minus xzy. So this we know nothing but y into zx minus zx. So what we have is y into zx minus zx into y, and we know what this is. This is nothing but y zx. Okay, so this is of course not going to be 0 in general, but again, unlike ka that we discussed, this has a nice structure, xyz plus yzx equal to yzx. And if I take it to the other side, so if I take it to the other side, what do I get? xyz plus yzx. Since I want to write it in the similar term, I can write it here that this is minus zxy Okay, so this is what we get, though we did not get proper associativity. Yeah, thank you. Now it says that we have unlimited time. So when we checked for commutativity, we saw that we got anti-commutativity, and when we checked for associativity, we get some other thing, and this is called Jacobi identity. So though we have a Lie bracket which is not commutative, not associative, it satisfies these two important properties. It is anti-commutative and it is satisfying some identity like this, xyz plus yzx plus zxy equal to 0. This is called Jacobi identity. I will still stress whatever I am mentioning. So okay, property 1 was anti-commutativity, property 2 is Jacobi identity. So though it is not commutative, not associative, unlike random thing like ka, that is why I introduced ka. So it satisfies some nice properties like anti-commutative and Jacobi identity. So this gives its own nice structure. And then it satisfies one more important property. By multiply by a scalar c, cxy is so if I multiply x, the first term, by a scalar c, it comes out nicely. Cxy becomes cxy. Similarly, x cy will be cxy. So multiplying one of them, either x by c or y by c, we get c times the Lie bracket xy. And the other interesting thing is when you add two things, x1 plus x2y, first variable only we are changing a sum of two matrices x1 plus x2, x1 plus x2y minus y into x1 plus x2. If I group the terms, I can write x1y minus yx1 plus x2 minus yx2. Just I have grouped the terms involving x1 and the groups involving x2. What we get is x1y plus x2y. And of course, similarly, if I keep the first variable fixed as x and in the second variable I write y1 plus y2, I get Lie bracket xy1 plus Lie bracket xy2. So most of you might know this is what is known as bilinearity. Bilinearity is exactly these four properties. Cx comma y is c times xy, x comma cy is c times xy, x1 plus x2y is x1y plus x2y, xy1 plus y2 is xy1 plus xy2. And of course, in case you have not seen, please note that so don't confuse this with the linearity. We are not changing both the variables at the same time. X1 plus x2, y1 plus y2 is in general not equal to x1, y1 plus x2, y2. You fix one variable and to the linearity and the other variable, then it is linear. So that is what is bilinear. You might have seen it in case of determinants. Determinant is the first place most people see multilinear maps and so on. So this is the third important property. It satisfies the Lie bracket that we defined. Anti-commutative, satisfies Jacobi identity, and it is bilinear. These are the three important properties it has satisfied. So one of the questions that biologists have been always asking, did chicken come first or did egg come first? Though they cheat a little bit and try to answer that egg came first, it is not clear which one came first. And for math students, whether a definition came first or whether examples came first. Though you may have doubts, unlike biologists, we have a definite answer. It is always examples that came first. So we had this example GLN with the Lie bracket satisfying these properties, and that is what leads to this definition. I don't want to call it as a bilinear form. So all the three properties we saw are satisfied for GLN and the usual bracket x bracket y equal to xy minus yx. Here it can be any vector space now, any map, whatever it is, satisfying these three properties, then it is called a Lie algebra. And of course, GLN, the only example we have seen, you can see that lot of what we call subspaces inside GLN also are going to be having the same property. So before we write, let me just give the definition. All you need is this closure axiom. If for any two elements in K, the bracket also is in K, then we can call it a subalgebra. And you can see that since this satisfies since the Lie bracket satisfies all those three properties, anticommutativity, Jacobi identity, and bilinearity for all the elements of L, naturally for a subset also is going to be satisfied. I should have mentioned here that A is a subspace of L, and we need a vector space, of course. So K should be a subspace of L, so vector space, and then the closure axiom for any two elements, the bracket belongs to that. Then naturally K is also the algebra. Okay, so all these examples people have seen lot of subspaces inside GLN which are going to satisfy all these three axioms naturally. What are all the examples that we can see? The easiest example is diagonal matrices. And of course, for diagonal matrices, something interesting happens. If we take the Lie bracket, what will happen? Matrix multiplication is not commutative in general, but if we take diagonal matrices, xy is going to be yx, so this is going to be 0. The Lie bracket xy is 0 for any two diagonal matrices, and naturally all we wanted was the bracket should belong to this. So this of course belong to diagonal matrix. So this is a subalgebra, and this is a special subalgebra leading to this simple definition. Diagonal matrices automatically give rise to this definition of abelian algebras. If the Lie bracket is 0, all these conditions automatically are going to satisfy. It's a trivial Lie algebra. Diagonal matrices are precisely that. And then the next important thing is SLN. Set of all n by n matrices with trace 0. We know that trace 0 matrices is a subspace. And what happens if I take AB in SLN and take the bracket? We want the bracket to be again in SLN, so trace of that should be 0. But not only for elements of SLN, we know that any two square matrices you take, trace of AB is going to be trace of BA. So trace of AB is 0. So again, the closure property under Lie bracket is satisfied for SLN. Trace AB equal to trace BA for every AB in GLN itself. And in particular, if you take SLN, trace of AB minus BA is going to be 0. So trace of the Lie bracket AB is 0. That is the definition of SLN. So the SLN is again a subalgebra. I've just given these two as a statement instead of checking this. It's easy to check, of course, that upper triangular matrices as well as strictly upper triangular matrices, they also will satisfy this Lie bracket closure axiom. So they will also be subalgebra. See, I want to concentrate much more on SLN and in particular SL2. SL2 is a very, very special object that we will be interested in. So it's interesting that just a small algebra like SL2 is going to help us a lot in future. The reason right now I will just give it slowly as time goes on, we will try to expand. So this is the reason right now I'm not going to explain it, but this is for future purpose. Many of the interesting Lie algebras are going to have lots of copies of SL2 sitting inside them. That is why SL2 is of special interest to us. So let us write down exactly SL2 what it is. It is set of all 2 by 2 matrices with trace 0. We know that set of all 2 by 2 matrices GL2 GL2 has dimension 4, and we are saying trace should be 0, so that brings the dimension by 1. In general also, if you take SLN, the dimension will be n square minus 1. And we will write a specific basis for SL2 and write down the Lie bracket among those basis elements. The standard basis, as it is called, this is what it is. H equal to 100 minus 1. See, the diagonal entries can be anything, but the sum has to be 0, trace 0. So if first one is non-zero sum C, the second one has to be minus C. So it becomes a scalar multiple of H. And upper triangular matrix 1, strictly upper triangular matrix is given by X, and Y is this. So this is called the standard basis of SL2. And let us see what is this going to be. First we calculate Hx. The definition, of course, it is Hx minus Xh. I have just written down the definition: 100 minus 1 into 0100 minus 0100 into 100 minus 1. If we calculate, what do we get? First entry is 0, second entry 1, this is 0, this is 0, minus first entry 0, second entry minus 1, these are zeros. So we have a 0, 1, 0, 0 minus 0 minus 1, 0, 0. So this is nothing but 0, 2, 0, 0, which is 2. Okay, H, X, Y, this is our standard basis. First we have calculated hx, that turns out to be 2x. What is hy? One zero zero minus 1 into 0 0 1 0 minus 0 0 1 0 1 0 0 minus 1. We get 0 0 here. We get minus 1 0 0 0 1 0 0 0 minus 2 0. This is minus 2. Sorry, minus 2. So hx was 2x, hy is minus 2y. What is xy? Zero one zero zero into 0 0 1 0 minus 0 0 1 0 into 0 1 0 0. First we get 1 0 0 0 minus this, of course, is going to be 0 0. This also is 0. We get 1 1 0 0 minus 1. H. So in terms of the basis elements, we have written down all the Lie brackets. See, we have those properties, bilinearity and anti-commutative. Since it's anti-commutative, it's enough if I write xh, hx and hy, we know what is xh, yhr, and when I write xy, we know what it is. So this is what we have got. So somehow these three important things will keep repeating in the next few lectures as well. Hx equal to 2x, hy equal to minus 2y, the bracket xy equal to h. Hxy, this is the standard notation. We are not going to change the notation for these three lectures. In general, any book you see, this is how it is going to be. 1 0 0 minus 1 is h, 0 1 0 0 is x, 0 0 1 0 is y. Hx equal to 2x, hy equal to minus 2y, xy equal to h. Okay, so from GLN, and we saw some various examples of subalgebras. We did not prove, of course, that upper triangular, strictly upper triangular are subalgebras. One can check it. We know that SLN is a subalgebra of GLN, and the diagonal matrices, of course, are important subalgebras. Diagonal matrices are the simplest example of abelian and Lie algebras. And SL2, as we are specially interested, as I said, it's going to come in handy in many circumstances. That's why we have written down SL2 calculation explicitly. Hxy is the standard basis, and all the Lie brackets are as it is given. Okay, so now this question. Does everyone agree with me that human beings are harder to understand than mathematical objects? At least I believe so. And what could be the reason for this? Anybody wants to say? Anyone interested in giving? Of course, only students. Any of the students here want to tell why it is true? If it is true, I suppose it is true. I believe it is true. I can give 1 minute or 2 minutes.
Because they are abstract.
Abstract. Human beings are more abstract, or mathematical objects are more abstract?
Mathematical objects.
Yeah, but still somehow I think that human beings are harder to understand. Anyway, we have kind of covered enough for the day, so we can
Sir,
try to
there are
answer
some replies in the chat box.
chat box. Many people have given. They don't talk by definition. Somebody said, you can just show the chat box. They are not defined, no specific structure. Sometimes what human beings are not well defined, sometimes not well defined. We can solve math problem and not emotional problems. Okay, a lot of interesting comments. Any more coming? I had said 2 minutes. I can afford to wait for 1 more minute. Of course, all of you know the answer. So when I say it, everybody will agree that one of the answers is almost correct. That's what I'm looking for. I shouldn't say correct. Okay, so somebody has mentioned that Mehul Maurya has said that sometimes what human beings say are not well defined. The simple fact is that human beings keep changing with time, unlike mathematical objects. Many of you might be having some childhood friends for 20 years, 15 years, and so on. Still, you can't tell what this person is going to do tomorrow, day after, mainly because of this particular reason. Younger people even more so, because you are all evolving as human beings, so you naturally will keep changing and hopefully changing for the better. But still, the way to understand both if you want to understand mathematical objects or human beings, the method is same. You can see how they interact with others. If you want to understand a human being, you can always observe how they interact, and that gives a lot about their character. And the same thing goes for mathematical objects, how two mathematical objects interact with others. That is what gives. So what do you mean by mathematical interaction? We all know how people interact. As somebody was mentioning about talking and things like that. Language is one of the ways we interact. So historically itself, they are known as compulsive communicators, and over the years they have developed so many ways to interact with each other, and that always tells about their character as well. So for mathematical objects, the way mathematical objects interact with each other is of course through maps, and you would have seen enough kind of maps. For sets, of course, it is just only a question of maps. Maybe you can talk about one map, onto map, bijective maps. Once you have come to groups, you know there is something called homomorphism and vector spaces, linear transformations. And for Lie algebras, see whichever structure you have, you would have seen in continuous functions between topological spaces, differentiable functions between maybe manifolds if you have seen. So many places, so many kind of maps we want. So in this particular case, since we are discussing Lie algebras, first of all, we need a linear transformation because we are in vector spaces. Apart from the vector space structure, which is addressed by the linear transformation, we have introduced this Lie bracket. That is what is the extra structure in Lie algebra. So any nice map should preserve that. That is what is the Lie algebra homomorphism. So for any two elements V1, V2 in K, T of V1, V2 bracket should be TV1, T1. So this is a natural way of defining. You know that so many cases, as I have said, you have all seen kind of maps. So this is the way to understand the abstract Lie algebras. We have two Lie algebras. How do we connect? Only through these maps, preserving the Lie algebra structure. And in particular, since GLN is what we are all very, very comfortable with, map to GLN gives a special name. GLN is what we are very, very comfortable with. So any map from K to GLN is called a representation of K. So the way to understand abstract objects is of course through the known objects. Since we think that we know GLN, we try to study homomorphisms from arbitrary Lie algebras to GLN. And I should have mentioned this earlier, but anyway, okay. Any bijective Lie algebra homomorphism is called an isomorphism. And once two Lie algebras are isomorphic, there is nothing much to choose from. You all know that only the names are different, but as objects, they are one and the same. And since we have been studying so many linear algebra, so I should define that also, sorry. Any subalgebra of GLN, all those things we have discussed, SLN, DON, upper triangular, strictly upper triangular, they are all called linear Lie algebras. And one of the nice things is that any finite dimensional Lie algebra is going to be isomorphic to a linear Lie algebra. So that is why it is enough if you understand what are linear Lie algebras or subalgebra of GLN, then you understand all Lie algebras, abstract Lie algebras, finite dimensional Lie algebras at least are going to be isomorphic to just linear Lie algebras. We have defined this Lie algebra homomorphism, and of course, two obvious maps, you know that zero map and identity map are obviously examples of homomorphisms. But the nice thing about Lie algebras compared to so many other things is that naturally there are a lot of Lie algebra homomorphisms, and actually in particular what we have defined as the representations, we will take it up tomorrow. Okay, enough for today. Anybody, any questions? Tomorrow same time, we are going to continue with homomorphisms, representations. Any questions? I am of course amused with Balu being there still. So everything fine? We meet tomorrow. Can somebody see chat box and tell whether anything else is there? Nothing is there, no? Anything from YouTube?
Not yet, sir.
So fine, we stop here and okay, the book.
Hey, Ilangovan, somebody has asked whether there is any book.
Yeah, I'm just writing it. I am also seeing that. I think the name is Lie algebras and representation theory. The Springer series, GTM series. Linear algebra, Anaga, I have just defined. Any subalgebra of GLN is the linear Lie algebra. Killing forms are we going to discuss? We have to wait and see. Applications, we will see. Given time, if there is a time. Okay, linear algebra I have answered. Book I have given. This is my reference book. Of course, this is my favorite book, but something else I have to tell. Tomorrow maybe I will tell something else.
Yeah, over to Bhumika.
Yes. Thank you for the lecture, sir. Now maybe we can all, have a group photo. So I request everybody to turn on their camera. So we'll have a group photo.
I should face the camera.
Okay, I'll be counting till 3, and then all of us will smile and there will be a picture taken. Okay? So 1, 2, and 3. Okay. Oh, there are still people. Okay, we'll maybe take one more. Okay. So again, I'll count till 3 and then we'll take a picture. Sir, can you face the camera, please? Yeah. Okay. So 1, 2, and 3. Okay. Thank you so much.
Thank you.
Okay. Thank you all for being a part of today's talk. A heartfelt thanks to Sir for explaining things so beautifully and making it so interesting. Again, a special thanks to Kumreshan Sir for being there. A special thanks to Professor Subramaniam for being there. It was really unexpected that you would be there and this talk would be so good. A special thanks to MTTS Trust and the organizing team. We'll meet all of you tomorrow. So you can all log out from the meeting. Thank you.
Okay, thank you.